Concrete is without any doubt a splendid building material. In one way, concrete is a very simple material. Anyone can mix water, cement and aggregates and finally obtain artificial stone with sufficient strength. In another way, concrete is an extremely complex material. No one fully understands the material and its complex behavior. This ambiguity of concrete makes it on the one hand the most used building material worldwide, and on the other hand a building material showing a lot of problems when not properly designed or placed. Traditional concrete needs to be compacted by providing external energy in order to remove excessive air bubbles and achieve adequate packing and optimal strength and durability. This can be achieved by means of vibrating pokers. When vibration is not properly done, the quality of the final concrete structure will be badly affected. In order to overcome the problems related to badly vibrated traditional concrete, self-compacting concrete has been developed, also called SCC. In simple words, self-compacting concrete fills the formwork like a liquid and does not need any external compaction energy. With SCC, the rheology or flow behavior of cementitious materials, including the behavior during pumping, has become increasingly important. In this context, some groundbreaking ideas have been proposed in a very ambitious research project called SmartCast. This proposal has the potential to create a paradigm shift in the construction industry. The problem while casting concrete is that the flowability of the concrete cannot be actively adjusted. The rheological properties to a large extent depend on the mix design. Once the concrete is mixed, it will show its rheological behavior, only further influenced by environmental conditions and duration of the casting process. The operator needs to passively rely on the rheological response of the fresh concrete and has only minor tools to intervene, for instance by increasing or reducing pumping pressures. Furthermore, small variations in concrete composition can have a significant influence on the rheological response of the fresh, self-compacting concrete. This leads to high-quality demands in the production plant when mixing the constituent materials, as well as on the construction site, while evaluating the workability of the delivered concrete. Major problems occur in practice with leaking formworks, blocking of concrete flow, and insufficient filling ability in case of congested reinforcement. These problems could be overcome by enabling an active control of rheology and stiffening of the fresh concrete. And that is exactly what the SmartCast project is about. Having obtained an advance grant from the European Research Council, Professor Geert de Schutter and his team are fundamentally studying the groundbreaking and challenging new ideas concerning active rheology control and active stiffening control of fresh concrete. The research is performed at the Maniel Laboratory for Concrete Research of Ghent University, one of the worldwide leading research institutes in concrete research. The main objective of SmartCast is to develop concrete with actively controllable rheology and stiffening in order to automate and optimize formwork-based concrete casting operations. In current concrete practice, the rheological properties of the concrete are defined by mix design and mixing procedure without any further possibility of actively adjusting during casting. The groundbreaking idea to achieve the main objective of active control is to modify concrete by adding special admixtures responsive to externally activated electromagnetic frequencies or other types of trigger signals. The principle of active rheology control can be illustrated schematically by considering a traditional slump flow test. In this test, a standardized cone is filled with fresh self-compacting concrete. The mold is released and the concrete is flowing, forming a cake-like shape on the base plate. The final diameter of this concrete cake is a measure of the flowability of the fresh concrete. A higher diameter represents a higher flowability. Consider a fresh, self-compacting concrete with some mixed-in responsive polymers. When no signal is given, the responsive polymers can be considered inactive. In this situation, the fresh concrete is showing a reference slump flow value while performing the slump flow test. When an external signal is now activated, the polymers show a response improving the workability of the fresh, self-compacting concrete. This becomes visible as an increased slump flow value. The rheological performance of the fresh concrete can be controlled by combining different types of polymers with different kinds of signals. Once the fresh concrete is in final position in the formwork, the flowability of the material is no longer needed. On the contrary, at this stage, a fast stiffening of the concrete is desirable in order to minimize the risk of formwork leaking and to reduce formwork pressure as fast as possible. This can be achieved by a second control feature called active stiffening control. Again, the desired control mechanism will be provided by a signal-induced response of some specially designed polymers added to the concrete. Consider again the slump flow test. When no stiffening signal is given, the concrete will flow upon removal of the cone mould, showing that the fresh concrete is still flowing and is not stiff yet. Activating the responsive polymers by an external signal before removing the cone will induce stiffening of the concrete due to the response of the polymers. In this state, the concrete will no longer flow when the cone is removed. The stiffening of the fresh concrete is externally triggered and the formwork is, in principle, no longer needed. The SmartCast project will fundamentally study different options of physical and/or chemical stimuli to achieve active control. This will enable faster formwork removal and will reduce the risk of formwork leaking and failure. Gaining the capability to actively control concrete rheology and stiffening during processing is a unique and challenging goal that will revolutionize the formwork-based concrete industry. In a next step, after successful completion of SmartCast, active control features can be implemented in the design of a 3D printing system. Approaching printing technologies from within traditional concrete technology is totally different from current approaches, copying layer-wise extrusion methods from other industries. Active control of fresh, cementitious materials is a prerequisite for successful 3D concrete printing in the future, whereas passively relying on autonomous stiffening or structural buildup will always remain an obstacle in current approaches. In this way, the SmartCast project will provide a fundamental basis for future-proof 3D printing of concrete structures.